it might take a little while. But I can do it from here also. So
Which, is it the
So
other below?
or maybe not.
Let's see. Well, the pointer is working. Oh, sorry.
That's okay.
Maybe
I'm going to do it
missing
from
the
here.
driver off.
Anyway, so today I'm going to talk about aerosols. Well, I know that usually not many people are used to this and know actually what I'm talking about. So first, why is it interesting to talk about it? Well, we can say the first thing is about climate change. I mean, about its implication in the climate model. And actually, it has two main effects. So one that are the direct effects. So basically, when you have a bunch of aerosols in the atmosphere, the first thing that it will do, it will block a part of the energy that is coming from the sun, because it's going to bounce back in space, or it can also absorb. So it affects the energy balance of the Earth. And the second effect is what we call the indirect effect, because the aerosols, so they can act like tiny nucleus or tiny seed to create clouds. So this happens naturally in the atmosphere, but because we are introducing actually more aerosol, this is an effect that is amplified. And so the first effect is because we are rejecting more aerosol in the atmosphere, then it creates more clouds. So it's blocking more energy from the sun. But the size of the aerosols also matters. So basically the idea is that the smaller the nuclei is, the smaller the droplet will be, and then the longer it will stay in the atmosphere, and then it will basically increase the lifespan of clouds, and then blocking out more radiation from the sun. Which is in a sense good, because this is somehow balancing out the effect of global warming. But there is another effect about aerosol. So it's responsible for about 400,000 deaths per year in Europe. And as a comparison, we have roughly 1,800,000 deaths due to cardiovascular diseases. So, well, you can say it's of the same order of magnitude, so it's still relevant to think about it if climate was not enough. So, what are we talking about when we are talking about aerosol systems? So, whenever you take a chunk of air in the atmosphere, what you will find is not only oxygen, nitrogen, and everything. You will also find other vapors that I have modeled with those small dots. And you will find also quite a lot of particles. And those particles, as I said before, so they may occur naturally. So those are the natural sources. So for instance, volcanic ashes or whatever. Or there is also a lot of anthropogenic sources, which which we could see as common of the system of the aerosol. So this is what we are talking about, and as you can see, it covers quite a wide range of sizes, from the molecule of vapors, which are basically below 1 nanometer in diameters, up to 100 micrometers for really large particles. So, well, we have to cover a really wide range of sizes. So, as I say, aerosol particles come in really different sizes, shape, mass, phases also, and chemical properties. But I'm not talking about all this. I'm just talking about one approximation of this. So the first thing is that I'm going to talk about a box model. So basically, I just well, the box model just means that all the properties are the same in all well, in all the location in space. I will also assume that every particle can be modeled as just a sphere. I mean an equivalent sphere with some quantized volume. And those volume will be actually exponentially spaced so that so that we can cover all the sizes that are of interest. Yes, and there is only one type of particle, so I'm not considering any chemical properties or anything. And also another assumption that is, I'm going to come back on it a bit later, is that when two particles collide, I mean there is only two particles that are colliding, they are not colliding between 3 or 4, we are just assuming between 2, which is actually quite a fair assumption. So this is what it will look like. So well, my model will be mostly applied for a chamber experiment. So basically, a chamber is like a big container in which you conduct some experiment. Then you can control what you are putting in. So you may have an inlet of particles, and you also have a measurement device that you are putting in this chamber. Or maybe outside, but I mean, because this is a box model, it doesn't matter where you put this measurement device. Okay. So one thing more is that we are not even trying to track every particles. We are just going to track a size distribution because otherwise it would be just it would require too many computers to do that. So then the idea is that at the beginning, you have like something that is almost continuous for the distribution, and then what we are going to use is only a discrete version of this size distribution. And so why we do that is, well, as I said first, it's computationally less demanding, and still we managed to get some good ideas about the microphysical properties. So that's why we are doing it. So now I will actually need some way to describe how this size distribution evolves. So for each bin, so each bin actually represents number particle concentration. So in the next slides, we are going to see how it evolves, and basically I'm going to tell you that it's depending on a lot of parameters. So basically the other bins of the size distribution, and probably on the pressure, the temperature, vapor concentration, and so on and so forth, and all the parameters you can imagine. So first, yes, we are also using these quantities because this is something that we can actually measure. The device that we are using to measure the size distribution is differential mobility particle sizer. And as a first approximation, you can divide it into two parts. Well, I know that if you are familiar with this device, I'm sorry. This is a really rough approximation. But basically, you have the first device that is the differential mobility analyzer, which basically acts as a prism for light. So it's just selecting what is the volume that you want to get from your actual distribution. And so once you have it, you have, I mean, the output of this device is basically something that is almost monodispersed. And once you have it, then you just have to count all the particles. And this is done with condensation particle counter. So basically, this is the model that we are using for the measurement. And for the next part of my talk, we will just use actually one matrix. So we will approximate it with a linear model, and for most of it, this H will be actually the identity matrix. And then there are some noise that are going to be added on it, and usually we assume that it is a Gaussian process. Even though it should be more like a Poisson process because it is counting, but well, that's good enough because we are counting like really large numbers. Okay, so the first mechanism that occurs is a mechanism that involves particle interactions. So as I say, we assume that when two particles are colliding, they are colliding only between two. So for instance, you have a bunch of particles in the air, and they are animated with some motion, and if you assume that this is a Brownian motion, then we talk about Brownian coagulation, as it is depicted here. So once two particles are colliding, then we are modeling them with another particle with an equivalent sphere. And so in this process, what is interesting to know is the frequency of the collision. And so I show you here the frequency of the coagulation for a Brownian motion. So as you can see, the frequency of collision will increase with the temperature, and it will decrease with mu, which is the viscosity. So just imagine if you are in a solid, then there is absolutely no collision happening. This is a case where you have the viscosity that is going to infinity. And it also depends on the size of the particles. So the next mechanism, so this is the interaction between particles and vapor. So in this case, I didn't dare trying to show any formula because there is a lot of different formula, but well, just depend on the case that you are talking about. But basically the idea is that when you have a particle that is suspending in the air, then you have some flow that is going toward the particle because you have a difference of concentration at the surface of the particle, because basically you have a null concentration on the surface and you have something that is not null outside, so you have a flow toward the particle. And well, this flow, or maybe the rate of condensation, is a function that will depend mostly on the diameter of the particle, the diameter of the vapor, the ratio of the mean free path of the particle, and the characteristic dimension of the problem. So basically here, mostly the diameter of the particle. And it will depend also on the diffusivity of the particle and on the vapors, and also on the concentration of the vapor, and so on and so forth. And well, have a lot of parameters. So that's not something that we are going to really use directly. I mean, there is nothing general about it. And finally, the last really important mechanism is the nucleation, or the generation of new particles of really small sizes. So the idea is that you have something that is roughly uniform at the beginning, I mean, in terms of vapor concentration, but you can have some particles that are coming somehow close to each other, and somehow something happens. For instance, like a photon is colliding with some cluster that is not too unstable, or some other vapor molecule is colliding with a cluster, and well, it changes the conformation of the cluster, and then it becomes something that is stable, and then from that you start accumulating more particles, and so this is like a new particle. Basically, we have again not a really good theory for that. I mean, there is a lot of work done with that, but the idea is that the nucleation rate, so the number of particles created per unit of volume and time, will be somehow a polynomial function of the vapor concentration. And well, there are the two first order are the main ones, and with the square one we will talk about kinetic formation, and with the linear one it will be more activation. So now that we have all this, so let's gather everything. So I guess I hope I will have enough time. So the variation of the concentration in each bin, it will depend on the coagulation, gain and loss, the condensation, also gain and loss, and some other terms that we are not going to consider here, but it's important to keep them in mind. So like dry deposition, like when the particle is just falling and then it's no longer an aerosol particle, or wet washing, for instance, when droplets are coming out of the cloud and taking particles with them, and other sources that include the nucleation, but not only. I mean, you could imagine in an experiment having an inlet and adding some particles that are not of the smaller size. So yeah, and then you end up with this kind of equation that is not really linear, but still it's not too bad because this is just quadratic. So yeah, so that's our model. That's our forward model, and this is with what I'm gonna play a little bit after. So now what? So now what's interesting to know is the growth rate. So that's something that depends on the condensation rate. It's important because it will determine how long a particle may stay in the air, and then in the end how it will affect the lifetime of a cloud, and also the nucleation rate, because this is the main sources of new particle in the atmosphere. So if we come back in here, so it means that we need to estimate the alphas and the J, because the coagulation coefficient, the beta, are pretty well known usually, well described by the theory.
Matthew, just to be able to follow, so in this equation X is the kind of, is it the
isn't
continuous or
the number? No. In this page,
it's
this
discretely size distribution, or the
yes.
one that you measure with the DMPS.
Yes, that's it.
Okay.
Yeah. So this is discrete because this is around one value, but it's
But you are not doing like in multi-line in 2001 that kind of having the cost set of, in a way, histogram of measured values and inverting it to a, let's say.
No. This is not.
continuous function.
No,
Okay.
that's not.
Yeah.
That's not how it works. Yeah. Okay. So, well, now the idea is to, as I said, retrieve those quantities, and how are we going to do it? Basically, we just use any inverse formulation, and here what we are going to use is the Kalman filter. So for those who are not completely familiar with this, the idea is that once you have an evolution model and a measurement model, so you can estimate the state of your system based on some observation, and so it's done basically in two steps. So one is the prediction, and so the prediction just say, okay, so with my model I try to estimate what I would have on the next step, and the filtering it just say, okay, so now I have my observation, and I have I predicted the observation, and depending on the difference between those two, then it will adjust, hence the name filter. So now this is the algorithm that I'm using. I mean, it's not exactly this one because, as you may know, you may have noticed, my model is not linear, so I have to actually use the Jacobian of my model. But basically, this is how I'm going to use it. But I'm showing you that because just to remind you, what we need in this model is somehow some guess of the initial state, and also some estimation of the covariance of the initial state. And we also need to know the covariance of the model, so how much do we trust our model, and the covariance of the data, so also how much do we trust our data? So now just an example of the data that I'm using. So this is 8 days that I am simulating with my model with vapor input that shows that on the 4 first days there is some event that are happening. So when I say event, it means new particle formation. And on the lower row, it's so here you have 1 day of simulation, and here you have 1 day of measurement at the Petiala station. And I mean, it's somehow quite a good model, but I mean, as you may notice, there are some phenomena that we are not accounting for, and this is mostly due to the fact that we are not accounting for the dry deposition and for the wet deposition and for other sink and source terms. But this is something that we are quite okay with that, with the model, because as I have mentioned, we also need some covariance of the model. And in this covariance of the model, it may also include sink term and source terms. And well, also for the, we also have the same for the measurement. But anyway, we could come on this later if we want. In my case, what I'm doing is for the first, for the guess of the initial state, I use directly the observation data, and I use the covariance of the noise, the one that I'm using for the simulation, as an estimation of the covariance of the initial state. And for the model covariance, I use something that is roughly this is a diagonal covariance. And basically we say that we believe our model the same way for each bins of the size distribution. But for the noise, we say, okay, so maybe we believe a bit less the measurement for the small sizes, and for the big sizes we will believe it more. So the diagonal is actually decreasing with the index. So here is the first result. Well, I have to speed up. So on the right you have the simulated data, and on the left you have something that is the output of the Kalman filter. And this is somehow better, even if you can see that there are some discrepancies that can be attributed to the convergence of the Kalman filter. But what is more interesting is that the maximum and minimum values are better in terms of comparison to the simulation. Also, if you take the evolution of 4 different bins, then you see that for the smaller sizes you have something that is quite smooth, because we explicitly say in the model that, in the measurement, that we are believing not so much the small sizes, but more the model. So the model will have a smooth evolution. But for the large sizes, then it completely follows the data. So now, for estimating the nucleation rate, we don't have any actual model. So what we are going to assume is that it may be modeled with a second order system, and it's going to be like a random walk, so with this term eta. And this is something that we are adding in the model. We are actually extending the model it will be in the Jacobian matrix. Okay, so basically for the size distribution we will have the same results, even though for the first bin we'll have more variation for the lower numbers. But what is interesting is the nucleation rate. So here I show you in green the simulation, and in blue and yellow what is the predicted step and the filtering step of the Kalman filter. And I'm somehow happy because when the nucleation should be 0, it's oscillating over around 0. And when I should have an event, then I start having something that is, well, that looks like an effect. So now we're doing the same with the growth rate, but I mean, I will spare you the details. And the idea is that, well, for the previous result, for the distribution and the rest, this is, yeah, and for the rest, this is really, really similar. But now we managed to retrieve both the nucleation evolution and somehow an image of the growth rate, which is actually the vapor concentration. And what is even more interesting is that in the model, we are assuming that we only have a nucleation that is a kinetic mechanism. And by fitting the output of the Kalman filter, so the data that you have in blue here, you somehow manage to retrieve the good coefficients. So, well, that's something that we are quite happy about. But, so as I said, I mean, we have something that is quite nicely behaved, but still we have like negative values for some concentration, which is not acceptable. And so the next step, I mean, the thing that I propose for next is some modification. I say, okay, so now I will split the spaces because for the size distribution, this is correct, I mean, like acceptable, but for the nucleation and vapor concentration, it's not really acceptable. So let's say that we separate those two spaces, and we will enforce a strict positivity constraint on the nucleation and vapor concentration. And for the other part, we are going just to use the Kalman filter. I will spare you again the details, sorry. But the idea is that, so when we are doing that, so we managed to retrieve actually some good values for the nucleation and for the vapor concentration. But when we have this, a similar level of noise as with the Kalman filter estimation, then we do not really manage to retrieve the good coefficients. So yeah, that's somehow a problem. Yeah, so this is still a work in progress, and we still have to account for real data. Yes, I still have to show that the algorithm that I'm proposing would converge. And for later work, what would be interesting is enforcing a strict positivity with the Kalman filter, also derive the Kalman filter for some Poisson process. And yeah, that's it. That's, yeah, thank you. I didn't give you much time for questions. I'm sorry.
Time for one big question.
Well, maybe I just bored you with what I said, sorry. So I guess there is no question.
Very, very interesting work. Are you later on, I mean, is it purpose to sort of include also this like a reconvolving the kind of rather costly collected size distribution data into the finer discretization, or is it basically kind of to employ the at the resolution of the kind of measured pins, so that you will have the identity in a way
that would be
between the unknown and the measurement?
Yeah, I mean that would be a possibility, but it's I guess it would require a lot of computational.
How's the resolution of the DMPS on this?
Well, basically you will use like maybe 40 beams spread from, for the best one, like from 1.5 nanometers, and you will go up to a few micrometers. But basically you will have to use two different devices, because you would need the one for the lower sizes, I mean for the small sizes, and the other one for the big sizes. Okay. So that's, yeah. And if you want to have something that is linear, well, you need a big cluster.
Okay.
Because you would need, I don't know how many billion, but I mean, you have to cover from 2 nanometers to let's say 2 micrometers, so 3 order of magnitude in terms of diameter. So in terms of volume,
Yeah.
you make the calculation and then you know why it's an exponentially spaced beams. Yeah.
Okay,
So,
let's thank Matthew again.